Cool. Let's get started. First, two announcements. First one, a note taker is needed for this class. So if you believe you take good notes, concise, clear notes, and you are willing to share, please visit ASU DRC's website. If you don't know where to find it, just Google ASU DRC and sign up as a note taker. So you can get $75 for stipend, and more importantly, you will get a letter of community service. So the second announcement, we post homework 1 online today. So you have 1 week to finish this homework. There are just 9 questions. Some of them ask you to crack some passwords, some multiple choice questions, and it's due next Wednesday, midnight. Please submit through Blackboard. So Monday we talked about data link layer security. We talked about up spoofing, how attackers can use up spoofing. So for the next week, we're going to focus on network layer protocol security and countermeasures. So we all know that many times the only network layer protocol we are using right now is IP. So this is not exactly true because we have several other protocols. They were there to help the IP protocol. For example, the ICMP, Internet Control Message Protocol. This protocol is used by network devices like any host and routers to send error messages. So this is not a protocol used for transmission. And the IP is the only protocol at network layer used for transmission. So we will talk about the security of IP and the security of ICMP in this class. So we already know that similar as the data link protocol, we have a broadcast address, like in Ethernet, we use OF as the broadcast address. So when a switch receives a broadcast message, it will forward this message to every host in the same network. And at the IP layer, we also have broadcast and also unicast. If the source IP address is like .2 and the destination address is .3, so this is a unicast message. This IP packet will only be sent from .2 to .3. If when .2 sends this IP packet, it will use 0.255, which is the last IP address in this subnet as the destination. It means this IP address should be sent to all the hosts in this IP network. So we will see how this could be used by attackers later. So this is what IP diagram look like. We already took a look several weeks ago. We have a source IP address, which is 32 bits for IPv4. We also have another 32 bits destination address. Today we will see several other fields. The first one is called protocol. Similar as the frame we discussed last week, in the frame there is a protocol fields. So when the operating system receives one frame, it checks the protocol fields to decide which handler should process this message. So the IP protocol, we have the same thing, and it specifies what is the payload in this IP packet. It could be number 1, which is ICMP, and it could be number 6, which is TCP, and also 17 UDP. So there are some other protocols which can be wrapped up using IP protocol, but we are not covering in this class. For example, OSPF, which is a routing protocol. So in this class, I do not plan to cover all kinds of routing attacks because we want to stay with the basics. So the second field is called a time to leave. So why do we need this field, and what does that mean? It's just 1 byte, first of all. So the role of this field is to ensure that a package will eventually be dropped. Why do we need this? So it's possible that some routers in the network, they form some kind of loop like this. Router A forward all the IP packets to router 2, and router 2 forward this to router 3, and router 3 forward to router 1. This is not supposed to happen in design, but it happens in real life. Maybe the administrators, they didn't configure the routers correctly. So this could cause a huge problem, because if a packet is sent from router A, and it will end up looping in this network forever. That's why we have a field called time to leave. How it works is every IP packet, it has this field, and this field specifies the longest path before this packet should be dropped. So how it works? So whenever a sender send out an IP packet, it will set this value. In most cases, it will be a small value like 64, which is big enough. Imagine that, I guess a lot of you know the small world model. So that model says, so from anyone in this world to another one in this world, there are only 6 hops. So imagine this is 1 byte, which means we can use 255 hops. If we apply the same theory into network, that's enough for us to deliver all the packets. So usually we set it as a 64 or even smaller. So whenever a router receives an IP packet, it will decrement this value by 1 before forwarding it. And if this value reaches 0, which means the router should not forward this, but just simply ignore this, drop this, and also send out a message to inform the original sender that I'm not sending out this, I'm not forwarding this IP packet because the time to leave value has dropped to 0. And another field is the header checksum, which is a checksum of the total header. So this should be easy to understand, but also very interesting. When a package arrives at a router, the router will calculate the checksum and compare the checksum. If the value do not match, it means the router should discuss this packet because something is wrong. So I have the first question for you is this checksum field designed to maintain the security objective of integrity? So what is the,
Integrity?
Integrity, yes. Can this checksum maintain that, help us?
I don't know, but it seems like it's designed to.
Obviously, it is designed to maintain integrity, but there are 2 kinds of different integrity.
Yeah.
Go ahead.
Versus an adversary, with some kind of adversary in the system, no. Versus system noise that you might pick up on a transmission, yes.
Exactly. So this is obviously designed for integrity, but it cannot maintain our security object integrity, which means this can defend some kind of intentional attack from attackers. Why? Because everything here is, there is no secret to calculate this integrity value, the checksum. So if an attacker wants to modify the package, let's say change the IP address, after the attacker changes that IP address, he can recalculate the checksum. So this checksum here can only detect the data corruption introduced in transmission, not really introduced by some malicious attackers. So this is where the IP diagram resides in a frame. So we have a frame. First, we have the data link layer, headers, trailers, and the whole part is a payload, which is the IP diagram. And the IP diagram will have IP headers and also IP payload. So the IP payload could be ICMP message, could be TCP message, UDP message. So it is worth noting that IP is the highest layer protocol which implemented at both routers and hosts. So you may see this figure somewhere. So here we have two hosts. They want to connect with each other. So they have the illusion that they are talking to each other at this IP layer. But actually, routers will also check the IP headers of the packet and forward the IP packet based on the IP destination address. And so router will implement this IP stack. However, switches, they work on this data link layer. They only look at the MAC headers. So I think, Eric, last Monday you asked a question why we cannot do the up spoofing on switch, defend that on switch, right? One of the reasons is if you want to defend up spoofing, you have to know IP address and MAC address. So traditional switches, they do not look at the IP address. They only know MAC address and physical address. But right now we have something like software-defined networking, and all those switches are smart. They can look at any field in a packet. So IP, it provides an unreliable and collectionless service. What do we mean by collectionless? So each IP packet is handled independently, and it is sent to the network independently. So there is no guarantee that the IP packet sent first will also arrive at the destination first, because they may even take different paths to reach the destination. So packets, they may be delivered out of order. And the IP is also unreliable because IP doesn't make any attempt to recover lost packets. There are many reasons to lose packets. For example, host A, it is not connected to any network. It sends out a packet through its adapter, but it is not connected to any network. Obviously, that packet will be lost. And there is no attempt at the IP protocol to recover that. And also, host A wants to send a message to host B, but host B is offline, or the host B's network is totally offline. Then there is no way at the IP protocol to recover that. That's why we have a new protocol, ICMP. This protocol is to help us. If something is going wrong with the IP, we use this protocol to report there is an error. So ICMP is an error reporting protocol for IP. When data diagram deliver errors occurs, ICMP is used to report those errors back to the source of the diagram. So ICMP doesn't correct that. It doesn't have the ability to correct that. So it will only report that back to the source, not to the router. So all the systems we are using right now, including our host systems and also our routers, they all implement ICMP. Use this to report all kinds of errors going on in the network, and also send out control messages. So it's very important here. ICMP doesn't really overcome the unreliability issues in IP. It reports that there is an error, but it doesn't fix it. So it is up to the upper layer protocol, for example, TCP, to fix that. So a host A sends out an IP package to host B, and find out this package is lost. The TCP will decide if I want to resend that package, not the ICMP. So ICMP Even though this is also a network layer protocol, it actually uses IP. Why is that? Because the ICMP messages has to be sent from host to host, or host to routers, or router to host. So in order to do that, you need the IP infrastructure to do that. But this ICMP is not used for transmission. It's only there to help IP. So in most literature, we say ICMP resides in the same network layer as IP. So we have the IP payload, and with IP header, there's an ICMP header and ICMP data. Sometimes we don't. In most cases, we don't use that payload there. So ICMP messages are encapsulated into IP diagrams. This causes a very interesting thing because ICMP is here to help IP to report problems, but it is using IP itself. Then it's possible that an ICMP message will cause another problem, which triggers another ICMP message. So this, to stop this, in the protocol, any error created by ICMP will not generate their own ICMP message. So which means if your ICMP message is lost, then there is no way for us to know that. If an IP message is lost, we may know that from an ICMP message, but an ICMP message is lost, there is no way for us to know that. So this is what an ICMP header looks like. First, we have this IP header here. We use all the IP headers. The ICMP payload. It's very simple, just several fields. First, the type of message, which indicates the type. Then code field indicate further information specific to that type. And the checksum, identifier, sequence numbers, and sometimes a payload, a very small payload. So we have prepared several scenarios for you to understand how this ICMP is used. The first scenario, let's say host A sends an IP packet to a destination host B. And A already knows B's IP address. That's why host A can construct that IP package. So in this case, let's say host B is offline. So instead of receiving this IP packet response, host A may receive a ICMP saying that I cannot deliver this message to host B. So there are basically one type called destination unreachable. And in this destination unreachable type, there are many subtypes specified by code. I choose two here. One is code 0 means I couldn't deliver this message because the destination network is unreachable. If code is 1, it means packet couldn't be delivered because the destination host is unreachable. So I have two questions. First, who will send out the type 3 code 1 message? Obviously, it cannot be host B because host B is offline. If it is online, it can send back the IP packet, not error reporting, right? So who can send out this? Normally, who will send out this? Router, but which router? There could be many routers in the past, right? Yeah? The first one. Oh, interesting. Any other? Okay.
Host A.
Host A.
When I'm pinging and I can't get to my host, it says that host A IP address responds back saying that destination unreachable.
Then how does host A know?
I don't know. It just says I just read the terminal. It just says host A IP address is.
Okay. So actually, the answer to this question is the last router. The router believes host B is in its network. So that IP package from host A eventually arrives at the router, and the router says, oh, this package should be sent to someone in my network. But then it checks, oh, in my network there is no one has this IP address, or it's offline. How he can check that? The router can send an ARP to say if that IP address has a MAC address live. So this is the first question, the last router. The second question, who will send out the type 3 code 0 ICMP message? Which means the destination network is unreachable. What?
First router.
First router, okay, that's possible. Any other routers?
Last router?
Last router. Maybe not the last router, because last router will send the first one, the type 3 code 1. So it could be any router in the past. When the packet, yeah.
So the router before last, because it's supposed to reach the last router?
Yes, but the last router actually controls the destination network, right? So if it reaches the last router, it means it already reaches the destination
Yeah, I
network.
said the router before last.
Yes, that's right. So every router before the last one, they could identify that, oh, I have no way to forward this. Okay?
Is that one-for-one ICMP message to failed IP delivery? Is it like one packet for one packet?
Yes. Yes. So going back to this question, so all the routers before the last one, they could send out this message. Somehow this package is delivered to this router to them. But however, they find out I have no knowledge to forward this. So I will send this back to the host saying that I don't know how to reach the destination network. So I believe you have been using ping. And the ping is a program to check if host B is reachable. So previously, host A is trying to send an IP packet, but we can explicitly send an ICMP package instead of IP package to check if a host is reachable. So if host A send out a type 8, which is echo request, code 0, ICMP message, it means the host A is asking host B, are you alive there? And if host B receives this ICMP message, it is supposed to reply with a type 0, code 0 message telling host A, yes, I am alive. And there are several different messages to do the same thing, just adding timestamp, and you see where you can add this in the ICMP data part, the payload part. So this is a screenshot of ping. So I pinged asu.edu, and it will keep sending ICMP packets until I stop it. So it will get the first. It will send a echo request, which triggers echo reply, and it tells me how long does it take for this round trip. So this is how ping works. And there is another very interesting application called Traceroute. So you are going to try this in our lab assignment. You are going to try all those things. So Traceroute can tell you a possible path a package takes between the sender to the destination. So why I'm saying a possible path, it's not the path, because IP is a collectionless protocol. And we say that it will treat each IP packet independently. So even if you are sending a file to your friends, using, let's say, UDP, which is just a simple ramp-up of IP, that packet may go through different routers. So all the packets for that file, the file will first be splitted into many IP packets. And those packets, they may go through different paths and eventually reach the destination. So using this traceroute, we are just getting one possible path between the sender and the receiver. So this is I use traceroute at home to collect to asu.edu, and we can see that you just need to traceroute and the domain name, and we get the first hop, which is 192.168.0.1. What is that IP address? Is it public, private? So it's a private IP address. So, and this is the first router. So this is a router I use at home. And then we have another 10.39.0.1. This is again another private IP address. So I'm using Cox at home. So this might be a private network set up by Cox. And after that, we have a 100.127.66.8, which is another router in the Cox network. And the fourth hop, eventually we arrive at here, 70.190.169, and you can see here, this IP, this router actually belongs to Cox. You can find this information online. And then this message is forwarded to the next hop, which is number 595 here. And you can see this IP address 68.1.1 is also a Cox router. So right now, my package is routed in the Cox, maybe their internal network. And eventually, this message leaves Cox network and collect to this router 192.158.140.253. So this is actually an IP address of a company called Cloudflare. So this company is actually a web hosting company. They are hosting ASU's website. So eventually, this is our destination. This is the ASU web server's IP address. So we first get to the web hosting company's router and eventually reach the ASU web server. So how does this work? So imagine how many messages we are going to receive if we send out a traceroute. If we do a traceroute, how many ICMP messages we are going to receive? Obviously, there is no centralized database or centralized party to tell us what the route is. So which means each router in this path has to send us a message. So I can forward your package to the next hop. So we are receiving like 7 messages here. So let's see how it works. So first, the traceroute will use the same as ping. It will use echo request to send out a echo request and to expecting to get something back. And it will also use another feature called time exceeded. So like we discussed before, when a router decrements the value of TTL, and if that value is 0, the router will send back a message telling the host the TTL is 0, has been expired, so I'm not forwarding this. So the time exceeded here is not really about time, it's about hops. So how it works? So traceroute will fool the routers and host to make this work. First, it will send out an ICMP echo request and set the TTL as 1. So what will happen? So this one, my laptop, send out ICMP with TTL1, and TTL is not a field in the ICMP header, but the IP header. So when my home router receives this message, it will first decrease it, then the value is 0, and it will not forward these IP packets, but it will send back an ICMP message which says time exceeded. So I send an ICMP to here and get another ICMP back. No package is forwarding to the rest of the network. So when my laptop receives this message, this message will, when the router sends back the time exceeded the message, it will put, because it's an IP packet, it will put its own source address and destination address. So the source address in this case will be the router's IP address on this port, not on this port. The port collect to the host. And the destination address will be my laptop's address. So when my laptop receives this ICMP time exceed message, I know that this message is sent from this router. The Traceroute will display that the first hop is this router, is this IP address. So now we know what is the first hop from my laptop to ASU's network. So the next step, the Traceroute program will increase this TTL value by 1. So in this case, the TTL value will be 2. And resend this echo request message. So first, it is sent to here, and here will decrease that TTL, but still it will be 1. So it will check its forwarding tables, routing tables, and decide, oh, I should send this to the second router. And the second router receives this message. And at this point, this message has been changed. The TTL is not the original value 2 anymore. The TTL is 1. So the second router will decrease that again, which makes the TTL value 0. And the second router says, since it's 0, I'm not going to forward this to the third router. I'm going to send back to the host ICMP time exceeded message. And in that message, it has the router's IP address. So when the Traceroute program receives this message, it will print out, oh, the second hop is this IP address. So funny thing here is, it is possible that the second hop is not directly connected to the first hop. It's possible that because you are sending 2 ICMP messages, it's possible that they are taking different routes. It's very possible, but we cannot tell that. So the Traceroute program will keep doing this until it get a message back from this destination. Why this destination will give a message back? Because this is an echo request, and the destination is supposed to give a echo reply back. So this is how Traceroute find a possible route between a host and a destination. So we talked about the ICMP, and we know how it works, and we see its applications to identify network errors. So how attackers can use this ICMP to attack systems? So first, attackers can use it for reconnaissance and scanning. So in any typical attack, the attackers, they will first engage in some kind of reconnaissance or scanning, so they can better understand the network topology, so they can better understand which host is actually alive. So that will be my attack target. If one machine is not even online, obviously I cannot attack it. So attackers could use this ICMP as a reconnaissance tool to learn about the network addresses. And after that, they can decide what kind of strategy I will use to attack some specific systems. And sometimes this can be also used for fingerprinting, which means I send out a message based on some side channels. Because some system may respond very fast, some system may respond very slow. Some system, when they respond, they will put something in the ICMP data field, and on other systems, they may reply with some different payload. We can use that to fingerprint what is the system is running on this IP address. So then decide what kind of attack strategy we are going to use later. So this is the first use of this ICMP message. So basically, this is not a vulnerability in the ICMP protocol itself. It is supposed to do this, but attackers can use this. Network administrators can also use this. And the second attack is called the ping of death. Well, the first attack. So this is a very old technique. It was used for back in the 1990s. So basically, the attacker does is the attacker will send out some malicious ping packet. So in the specification, the ping packet should only be 64 bytes because it's not giving some payload. It's not necessary there. But some people find out if you send a huge ping packet, and when the host receives that packet, try to pass that packet, the system will crash. The reason is those systems, when they implement that, how to handle ping packet, they were following the specifications, which says the ping packet should only be 64 bytes. So if you're sending a big one, if they are on string copy, there might be a buffer overflow, which crash the target system. So the root cause of the problem is not really the ICMP protocol, but it's more software vulnerability in the target machine. And because they were not designed to properly handle huge packets. So this one can be easily fixed. What you can do is you just upgrade your operating system to make it either drop those malicious packets or response it. However, in most cases, because the specification says the ping packet should be only 64 bytes, and if you receive a huge ping packet, it means someone is attacking you. But this is can be easily fixed, so it's not a huge problem. And a second attack, we call it ping flood. It also worked before. The idea is very simple. If you are the attacker, you just send out a lot of ping package, maybe huge ping package, to the target. So you will block the target's network. It worked before back in the 1990s because everyone has a very slow internet connection. So if an attacker has more bandwidth than the victim, for example, the attacker used DSL line and the victim is using a dial-up model, they can pull off this kind of attack. However, everyone now we will have a high-speed internet, so this is not working anymore. And the third one, very interesting. This one is related to the protocol itself. So this attack is called the Smurf attack. So to pull off this kind of attack, we also need to spoof the IP address. So in this attack, a spoofed IP packet contains an ICMP echo request message with a source address equals to the attacked system, the victim. So anyone in this network, let's say this is the attacker. The attacker will send out a lot of, actually in this case, we're just sending out one echo request message to a whole innocent network. However, this echo request message was spoofed. we changed the attacker's source IP address with the victim's source IP address. So everyone on this innocent network, when they receive this echo request, they thought this victim is asking for an echo reply, but actually it's not, it's the attacker. So to pull this off, attacker can send a lot of messages to all the machines here, but it's not effective because you may want to send that to 10,000 of computers. So the attacker can utilize the IP broadcast address. We'll send out echo request to an IP broadcast address, so every host in this broadcast domain will receive this message. So when they receive this message, they will reply back to the victim. And why this is more effective than the ping flood? Because ping flood, we're talking about just one host, one attacker trying to attack the victim. So even though that attacker can try to send out messages as fast as possible, but still, there are not many. But in this case, if we have a huge innocent network, like ASU's network, we're talking about 10,000 of machines, or maybe more, hundreds of thousands of machines, sending out a reply message back to the victim directly. So this attack was discovered also back in, I think, like 1990s, I guess, or early 2000. So it might be a very early distributed denial of service attack, because we have many hosts. They are participating in this attack. So how to defend this? This can be easily defended too right now. First, let's say this is ASU's network, and we can set up a firewall here. So the firewall will first block any ping like this. I do not, my firewall do not allow any ping. That's possible, but which means all those hosts in the network is not going to send out any echo reply. So we cannot use this for web server or something like that. But if it's a production network like an ASU network, why we want to expose our IP address to the outside world? We don't want that. So we can set up a firewall here to disallow a ping message from outside. We can also disallow ping message, the ping echo reply message originating from our network to the outside, because we don't want to do that. And another way to defend this is, even if we allow ping, so anyone from outside world can ping us, we can disable the echo reply with broadcast address. If you want to ping me, it's okay, but you have to give me a unicast message. So you have to specify which IP address you want to ping, not a whole block of IP address. So this is how we can defend against Smurf attack. So this kind of attack, we need to spoof the IP packet, which we will talk about in the next class, because that's a fundamental vulnerability in the IP protocol, which is the IP address is not authenticated. So starting from next class, we will talk about IP and IP attacks. And after that, hopefully it can motivate you about IPsec. Nope.
No?
Nope. Yep.
I won't be here Friday. I'll be out of town.
Okay.
Am I missing anything important?